Have you ever looked at a massive skyscraper or a huge bridge and just wondered, how does that stay up? I mean, what's stopping it from just collapsing? Well, it all comes down to the physics of staying perfectly still. It's a concept called static equilibrium. So let's dive into the incredible science of how things manage to stand their ground.
I mean, just look at this. This incredible balancing rock in Colorado seems to completely defy gravity, right? But it's been sitting right there in what physicists call static equilibrium for literally thousands of years. So what's the secret? What is actually keeping it from tumbling over? That's the big question we're going to tackle in this explainer.
All right, so to figure out how that rock stays put, we need to get into the science of being motionless. It's a field physicists call static equilibrium.
Now, you might hear the word equilibrium and think it just means perfectly still, but it's actually a little broader than that. In physics, it means an object's momentum, both its straight-line motion and its spin, isn't changing. So yeah, that could be a book sitting on a table, but it could also be a hockey puck gliding across perfectly smooth ice at a constant speed. But for what we're talking about today, we're going to zero in on that staying perfectly still part. That is what static equilibrium is all about. The object isn't moving from one place to another, and it's not spinning around. It's completely, totally at rest, just like our balancing rock.
But here's a really crucial point. Not all stillness is the same. There's a huge difference between stable and unstable equilibrium. Think about a marble at the bottom of a bowl. If you give it a little nudge, it just rolls back to where it started. That's stable. But what if you balance that same marble on top of the bowl? The tiniest push, and it's gone. It moves even further away. That's unstable.
And this domino is the perfect way to see that in action. Look at the one on the left. It's balanced perfectly, right? Its center of mass is sitting directly over that tiny little supporting edge. It's in equilibrium, sure, but it is incredibly unstable. And you see what happens on the right? The slightest tip and gravity creates a twisting force. We call that a torque that sends it toppling over.
And this isn't just for dominoes. You know, it applies to us too. Take this construction worker. When his feet are parallel to the beam, he's got a really wide, stable base. He's solid. But if he turns 90 degrees, his base of support gets super narrow. All of a sudden, he's a lot less stable, kind of like that domino, and way more vulnerable to, say, a gust of wind.
So how do engineers make sure that bridges and skyscrapers are stable and not like that domino on the edge? Well, it turns out they follow two incredibly important fundamental rules of balance.
Okay, let's break this down. It's actually pretty simple. Rule 1. You have to balance all the forces. That means every single push and every single pull acting on that object has to add up to 0. They all have to cancel out. Rule 2. You have to balance all the torques. Every twisting force also has to completely cancel out. For something to be in true static equilibrium, both of these things have to be true, no exceptions.
And here's how physicists write that down in their language. Don't let the symbols freak you out. That Greek letter sigma just means the sum of. So this first one just says the sum of all the forces, F, has to equal 0. And the second one says the sum of all the torques, which we write with the Greek letter tau, also has to equal 0. That's it.
Now, calculating the torque from an object's own weight could be ridiculously complicated, right? I mean, gravity is pulling on every single atom. So physicists came up with this really clever shortcut. Instead of worrying about all those atoms, we can just pretend that the entire force of gravity acts on one single point, and we call that point the center of gravity. For pretty much any object you'll run into, it's the same as the center of mass.
So let's put this all together with a classic example, the leaning ladder. To figure out if it's stable, an engineer draws what's called a free body diagram, just like this. And if you look, you can see all the forces. You've got gravity pulling the ladder and the firefighter down. Then you've got the wall pushing outwards. And down on the ground, the pavement is pushing up while friction is pushing in to keep it from slipping. For that ladder to stay put, every single one of these forces and all the torques they create have to perfectly, and I mean perfectly, cancel each other out.
Okay, so we've got our two golden rules. Net force is 0 and net torque is 0. That should be enough to solve any static problem we come across, right? Well, not quite.
I mean, think about something we've all experienced, sitting at a wobbly four-legged table. If we have these two fundamental rules of balance, why can't we just use them to calculate the forces on each of the four legs and figure out what's going on?
Well, the reason is because this table is what engineers call an indeterminate structure. And honestly, that name kind of says it all. The forces are literally indeterminate, as in we can't determine them, at least not with the rules we have so far.
So here's the mathematical trap we've walked into. We have 4 things we don't know, the upward push from the floor on each of the 4 legs. But our rules of static equilibrium only give us 3 equations to work with. Think about it. We can say all the forces left and right have to balance, that's 1, all the forces up and down have to balance, that's 2, and all the twisting torques have to balance, that's 3. And that's it. We've got 4 unknowns, but only 3 equations. You can't solve it. We're stuck.
So what are we missing? What's the secret ingredient that solves the puzzle? Well, the solution comes when we realize that objects in the real world aren't perfectly rigid. They bend, they stretch, they compress. The key is elasticity.
Elasticity is this really fundamental property of pretty much all materials. When you apply a force to something, it deforms, just a little bit. And as long as you don't push too hard, it'll spring right back to its original shape when you let go. And believe it or not, this simple idea is the missing key that solves the entire wobbly table problem.
So what does this look like way down at the atomic level? This model is a fantastic way to picture it. You can imagine a solid object as a grid of atoms all connected by billions and billions of tiny stiff springs. So when you pull or push on a material, you are literally stretching and compressing all those atomic bonds. The stiffness we feel is just the collective force of all those springs pushing back.
Now, physicists like to classify these forces in deformations into 3 main types. First, you've got tensile stress, which is just a fancy way of saying pulling or stretching, like a rubber band. Then there's shearing, which is that sliding or slicing force, kind of like what scissors do to paper. And finally, there's hydraulic stress, which is that uniform squeeze a submarine feels when it's deep underwater.
So how do engineers figure out a material's limits? They use this, a stress-strain curve. Basically, they pull on a material and measure how much force or stress it takes to stretch it by a certain amount. That's the strain. This graph tells them everything. It shows the elastic range, where it will spring back, the yield strength, where it starts to permanently deform, and finally, the ultimate strength, which is the point where it just breaks.
And that right there brings us all the way back to our wobbly table. The wobble happens because one leg is just a tiny bit longer. So when you put something heavy on the table, that longer leg has to compress more than the others. And because it compresses more, its internal atomic springs push back with a greater force. This direct link between how much a leg squishes and how hard it pushes back gives us the extra information, that missing 4th equation that we needed all along. All of a sudden, the problem we couldn't solve becomes solvable.
So you can see, this isn't just about wobbly furniture, right? These 2 ideas, equilibrium and elasticity, are completely interconnected. And together, they are the absolute foundation of how we build and engineer our entire modern world. So the next time you see a skyscraper gently swaying in the wind, or feel a bridge bounce just a little as you drive over it, remember this beautiful paradox that's at the very heart of engineering. To be truly strong, a structure can't be perfectly rigid. It actually has to have the wisdom to flex. It has to bend a little so that it will never, ever break.